Okay, this is the last video on probability. So in this video I'm going to talk about mutually exclusive events and independent events. And each of those could come into Venn diagrams, tree diagrams, all the things that we've done so far. Independent or mutually exclusive events could be brought into any of those. Just going to look at mutually exclusive events first. So two events, A and B, are said to be mutually exclusive if they have no outcomes in common, or if it is impossible for both of them to happen at the same time. So if they cannot happen at the same time, then the intercept will be 0. The Venn diagram will look like that, so there will be no overlap. So if you see a Venn diagram and then there are two circles in it that are not overlapping, then you know that both of those must be mutually exclusive. And then in terms of the addition formula, well, if this is 0, the addition formula, which is usually this, probability of A plus probability of B minus the intercept, because this is now 0, the addition formula becomes that. Okay, so you might be told that two events are mutually exclusive, in which case you know those two facts, or alternatively you're going to be asked to show that two events are mutually exclusive, so you either need to try and show this, or you need to try and show this, depending on the numbers you've got. Okay, so it's going to be two, they'll either tell you, or you'll have to show that it is. Just here's some examples. So we've got a bit of a spinner. So this is supposed to be a spinner with 4 different colours and numbers on. Okay. An example of two events that are mutually exclusive. Well, the probability of a red and the probability of a blue. From one spin, you can't land on a blue and a red at the same time. So those are examples of two events that can occur at the same time. Another example of mutually exclusive, probability of a green and the probability of getting a 1. Those two events are mutually exclusive. They cannot occur at the same time. Two events that are not mutually exclusive, the probability of getting a red, the probability of getting a 2. They can occur at the same time because from one spin it could land on that section there where it's both a 2 and a red. Okay, so those are just examples of mutually exclusive and what's not mutually exclusive. Okay, again, you can think of it in terms of packs of cards. The probability of getting a diamond and the probability of getting a heart from if you choose one card is mutually exclusive. If you choose one card, the probability of getting a heart and the probability of getting a queen, those are two events that aren't mutually exclusive because from one card you could choose the Queen of Hearts. Okay, so those are examples of what are and aren't mutually exclusive. If they can't occur at the same time, then they are mutually exclusive. Okay, so just a few questions to do with that. Events A and B are mutually exclusive and the probability of A equals 0.25, the probability of B equals 0.4. Work out the probability of A union B. So we don't need a Venn diagram particularly, but I'm just going to draw one. So because you are told that they are mutually exclusive, then your Venn diagram would look like that. Okay, so the union is just going to be the 0.24 plus the 0.4, which is 0.64. The probability of B intercept not A, well, usually that would be a moon, the moon of B if there was an overlap, but there isn't an overlap, so where is B intercepting with not A? Well, it's just B, so that's 0.4. And then everywhere outside, 0.36, or it's 1 minus the union. Okay, so that was relatively straightforward. We'll look at mutual exclusivity in some other examples later. I'm just going to talk about independent events. So we've looked at conditional probability in more depth. So conditional probability is dependency. So if one thing is dependent on the other, and that gave us our multiplication rule, which was that. So that was for dependency on conditional probability. If two events A and B are independent, then the outcome of one event does not affect the outcome of the other event. So rolling 2 dice, the probability of getting a 6 on the second die is independent of getting whatever you get on the first die. It has no bearing on it. So the probability of A occurring is the same whether B has occurred or not. Now this means that the multiplication rule that we use for conditional probability is now adapted to that because of this. So because the probability of B given A is the same as the probability of B, because B is independent of A. So this has no effect on this. So that must be true. If that is true, then that is just the probability of B, and we get that. So that is an adaptation of the multiplication rule. Okay. Now again, you could be told that two events are independent, in which case you know that you can work out the intercept. So in this case there is an intercept. Notice this is not going to be 0. Unless one of these is 0, then this isn't going to be 0. So do not get mutual exclusivity and independence mixed up. Okay, this is always going to have a value unless one of these is 0, and then it's pointless anyway. If you are told that two events are independent, then you know you can multiply the two things together to get the intercept. Okay, so you may be told. The alternative is where they ask you, and they'll do this quite a lot, is to ask you to prove whether two events are independent or not. Okay, what you should never do is assume. That's a common mistake. So only use this rule if you are told that they are independent. Never assume that they are. If you have to show that two events are independent, usually you're going to show that this is true. Alternatively, you need to show that this is true. Okay, so to put that into practice, a few questions. First one, probability that Bob has coffee in the morning is 0.4. So the probability of coffee, sorry, not 0.4, 0.8. The probability that he has toast in the morning is 0.3. And the probability he has both, so the probability he has coffee and toast, is 0.24. Are the events having coffee and having toast independent or not? Well, if you work out the probability of C times by the probability of T, that's 0.8 times 0.3, which is 0.24. So therefore, dot dot dot. Therefore, the probability of C times the probability of T equals the probability of C intercept T. Therefore, dot dot dot, events C and T are independent. So we've shown that those two probabilities timed together gives the intercept. Therefore, that rule is true. And if that rule is true, then that means that they are independent of each other. Okay? So just because Bob has toast in the morning doesn't mean that means he's going to have coffee. They are independent choices. Okay? The Venn diagram shows a number of students in a particular class who watch any of three popular TV programs, A, B, and C. Find the probability that the student chosen at random watches B or C or both. So that in symbols, B or C or both is B union C. B union C, 4 plus 5 plus 10 is 19, plus 7 is 26, out of a total of 30 students. And then determine whether watching A and watching B are statistically independent. So this is a sort of classic question. Are those two independent? So we've got to go through a sort of standard way of proving it. So for B, I'm going to write down the probability of A, which is 7/30. I'm going to write down the probability of B, which is 19/30. And I'm going to write down what the intercept, which is 4/30. And then we need to show either the product of those two is that, or the product of those two is not that. So if we do probability of A times the probability of B, so 7/30 times 19/30, well, that's 133/900, which is not that. So we can say probability of A times the probability of B is not equal to the intercept. Therefore, A and B are not independent. Okay, so in the context, because the student watches A, then that means they are going more likely to watch B. It's dependent. Perhaps they're similar programs. Okay, so you've got to show, if you are proving something, that they are independent or not. You've got to show the same approach. So you're basically either showing that this is true, that these two equals that, or these two don't equal that, and then you need to make some sort of final statement to say whether they are independent or whether they're not. Okay, and then incidentally, it doesn't ask, but here, A and B, because there is an overlap, they are not mutually exclusive. B and C, there's an overlap, they are not mutually exclusive. But A and C, because they don't overlap, then we can say events A and events C are mutually exclusive. They don't overlap each other. And that's a common way of drawing a triple Venn diagram if two of the events are mutually exclusive. Okay, don't draw it like that and then have a zero somewhere. So if you know that two events are mutually exclusive, then generally draw them in a line like that. Okay, pause the video and have a little go at those two questions which are in your booklet. Okay, so first one, probability of A times B is 0.18 and the intercept is 0.18, so therefore A and B are independent. Second one, probability of P times Q is 0.08, so that is not, those aren't independent. Probability of Q times the probability of R is 0.28, which is the same as the intercept. So Q and R are independent of each other. So P and Q are not independent, R and Q are independent, and the two events that are mutually exclusive are P and R. Okay, we're just going to look at a couple more examples where we have questions about independence and mutually exclusive events, and then you're going to do the exam questions. So a red die and a blue die are rolled and the outcome of each die is recorded. A is the event, outcome on the red die is 3. B is the event, the outcome on the blue die is 3. C is the event, the sum of the outcomes on the die is 5. And D is the event, the outcome on each die is the same. Show that A and B are independent. So there's the sample space. A is the outcome on the red die is a 3. Okay, the probability of that happening is on the outcome of the red die being a 3, so is a 6th. And then B is the outcome on the blue die is a 3, so the probability on the blue die, out the event 3, that's also 1 in 6. The probability of getting a 3 on the blue die and a 3 on the red die, well, 3 on a blue, 3 on a red, is 1 out of 36. So you can see that the probability of A times the probability of B is equal to the intercept. Therefore, A and B are independent. Okay, and then for part B, C and D are mutually exclusive. So if they're mutually exclusive, they can't happen at the same time. Either we need to show that there's no intercept, or we need to show that the union is just one plus the other. So C is the event that the sum of the outcomes on each die is a 5. So where are the outcomes on each die of 5? There. So the probability of C is 4/36. And D, the event on each die is the same. Well, that's there, 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 and there. So the probability of D is 6/36. The probability of getting a sum of a 5, or the numbers being the same, is all of those, which is 10/36. So we can show it by saying probability of C union D is probability of C plus the probability of D. But I mean, you can physically see that there's no overlap because those are totally different to the 5. Okay, but you can't really say that in a sentence. So this is what you need to show in terms of maths. Therefore, C and D are mutually exclusive. Okay, so this is what you need to show in terms of the maths, although you can physically see that there's no overlap. Okay, and then we're just going to look at a tree. Mr. Dixon plays golf. The probability he scores par or under on the first hole is 0.7. If he scores par or under on the first hole, the probability he scores par or under on the second hole is 0.8. If he doesn't score par or under on the first hole, the probability he scores par or under on the second hole is 0.4. Draw a tree. So he's either going to score par or he's not on the first go, and then he's either going to score par or under or not, par or under or not on the second go. So I'll call it P, not P, P, not P, P, not P. If he scores, suppose that he scores par or under the first hole is 0.7. That's 0.3. If he scores par under the first hole, the probability he scores par under the second hole is 0.8. And then if he doesn't score par or under on the first hole, the probability he scores par or under the second hole is 0.4. So there's the tree. State whether the events scores par or under on the first hole and scores par or under on the second hole are independent. Okay, if they were independent, these two would be the same. Okay, so state whether the events first hole or second hole are independent. They are not independent because the probability from one branch to the second branch is different, which means that that must be dependent on that. Okay, so that's, I mean, I probably should use a different letter to write it in symbols, but that's ultimately what it means. So the probability that he scores par or under on the second hole, if it was independent, would be the same as the probability he scores it on the first hole. So write something along those lines. C, find the probability that Mr. Dixon scores par or under on only one hole. So he's either going to, I'll put a 1 there actually, second hole. So par or under on only one hole, so he's either going to get par and then not on the second, or he's going to not get par on the first and then get par on the second, which is 0.26. Okay, so again, they're asking about independence. You can just see that from the branches would have the same probability if one thing was independent of the other one. Okay, so there are 2 exam questions to have a go at. Those 2. And then there are some questions on mutually exclusive and independent events. So these ones are the ones that we skipped out earlier on because they mentioned independent and mutually exclusive events. So I'd like you to go back to these ones. So these ones are year 2 questions, so those are a priority. If you want to do slightly easier questions, then have a go at some of those first. But these are compulsory. These ones, I would say, are optional. These are easier than these ones. And then there's one little review question that you can have a go at. So make sure that you've done all the questions from the exercises and have a go at the exam questions. Your teacher will have the solutions to the exam questions, so when you're done, when you've done them, you can ask your teacher. And that's the end of that last probability video.